Record on this computer. Okay. Yes. Is it showing? Yeah, it's recording. Okay.
Thank you.
Yes. So what it says, you have had 10. So you have had f of t, which is determinant of a minus ti. Your question is why determinant of a is the same as f at 0 is the same as a naught. Is that true, Brian? Are you there?
Oops. Can you try again?
Oh yeah, you can hear me. I didn't mute it. Sorry. Yeah, that's the problem.
So that's just your question right over here. Oops. I have to maximize right over here. Why this is true?
So yeah, is the determinant, why is the determinant equal to the 0 there? Equal to the characteristic polynomial evaluated at 0.
This one given in the problem or not?
No.
And this one.
Oh
This
yeah.
One definition of a characteristic polynomial,
because
right?
this is really same as what it's over here, because when you plug in f at 0, then this is determinant of a minus 0i, which is the same as determinant of a. And then if f of t is just, f of 0 is just really a polynomial of whatever degree is, when you plug in 0, this is the same as a naught. So that's just why this is true. Is that true?
Yeah, because a is invertible. So determinant of a had to become different from zeros. So that's why a0 different from 0.
Brian, can you use your pen here to just show where you are at and what was exactly? I mean, try to write on my board.
So I can't write on your board while you're screen. Oh, okay. No, you're on OneNote now. Okay, then let me see.
I mean, that's easier for all of us. If you have, I mean, anyone else, if you have question, write on my board. That's easier when you read the problem. Anyone else can just follow what you are talking about. So that was problem number 20 of section 5.1, and this is assignment.
So this says specifically I can't share while you're sharing.
But can you use your pen to write? You don't need to share. Use your pen to write.
No.
That was okay last time. Okay, so I think this should be here. And that should be the setting. Did you test over there? Do you see where? No,
I'm not familiar with Zoom that well, so I don't.
That's fine. Don't worry. Okay, so because if we can use those things, it says annotate on top of the Zoom, and then if you bring down that bar, it has all the options that you can write it. Anyone else, like Kimberly, Juan, can you try to write on my?
There we go.
Who is writing?
So that's me, but
okay.
I'm not going to be able to write with my mouse anything. I
oh yeah,
can't.
So you don't have. Okay, that's.
I tried this, but I cannot try this.
Okay,
I tried it, but I cannot.
It's fine, because I thought in this way you can write the problem, then everyone else can see what the question is. But here, don't worry, then I will write the problem. Okay, so whatever you wrote, you need to erase it. I can't erase it. Do you know? Okay, so now about the question, did you just figure out what's just easily no to get it out?
I mean, I have my work here. If you want me to show my work, I can set that up on the webcam.
So I stop sharing, you will share? Because the question was really why this is true, right? So the question is why this part is true.
Correct. I do, yeah.
So that basically is coming from right over here, that you have to plug in t equals 0, and that's just really where the f of t equals determinant of a. Is that okay, Brian?
If f is 0. Oh my god. Oh my god.
That's so easy, right?
Okay, I'm gonna turn it in now. I'm so sorry to keep you waiting.
No worries, okay? This is not really something that you could guess from the beginning, but that's fine, okay? So if I answer your question, I can move on to the next question.
Yes, go ahead. I don't know if I have any more
Okay,
questions.
who is the next person? Next question, guys. Should I check the chat? Anyone said anything to the chat? No. Any question about any of the problems that you have? Okay, so this is just really question answer session. There is no teaching. If you have question, I'll answer them. Anything? So let's just try. For example, if I can bring the take-home test of last semester here, then at least we can practice with those problems. Where are them? Let me find out where are them first. I have to go to the
Okay, I've got one.
question.
Is 3.3 9. It says prove that the system of linear equations ax plus b has a solution if and only if b is in the b is in R of LA.
So
B is in the range of LA. And I guess I could probably figure it out on my own actually.
if you, okay, should I find the problem or not? Okay, so let's just let me find out that which one I can just try it here. At least when you are on line, we can practice some extra problems. So this is, I think I can do.
I mean, if of the problems I've done, I thought the most interesting one was number 17, and it's in 3.2.
Mm-hmm. Can you explain or?
Yeah, I can explain it. I won't. You know, actually, if you want me to show the work,
Yeah.
just
Okay. So then I stop sharing. You share it. Okay.
Okay. Let me set it up here.
I'm looking for extra problems at the same time.
Oh, no, I don't want to share the screen. What is it? Start video. Video settings. Mirror. And let's see what's going on here. No, that should not be mirrored. So, okay. And then probably just want. One more thing. I'm sorry everyone's getting motion sick about this. I'm going to figure this out one day. Right now, I just have to hold this. Okay. And I don't know if you can make that. If you can make that. Oh, yeah. Okay. I pinned it. Okay. That's not bad.
If you don't move your hand, that's not bad. We can see it.
Okay. Okay. So what it's asking is that prove that the system of linear equations ax equals b has a solution if and only if b is an element of the range of, no, that's the wrong problem. Okay. I'm sorry.
No.
It's a disorganized day. You really get punished for not being organized. Here we go. I'm going to get a little stand for this thing. This is problem 17. Prove that if B is a 3x1 matrix and C is a 1x3 matrix, then the 3x3 matrix BC has rank at most 1. And conversely, show that if A is any 3x3 matrix having rank 1, then there exists a 3x1 matrix B and a 1x3 matrix C such that A is equal to B, C. So, number 4. Did I just show the first part? Oh yeah, no, okay. So basically, like, what I did was I started with 2 arbitrary. Really? The sun's gonna do that? Oh gosh, that's so. It's the cloud, everyone. Really? That's so bad. Okay. Here, maybe I can go closer. So I started with two arbitrary vectors, right? And I multiplied them together in a way to get a 3x3 matrix. So the column vector is on the left, the row vector is on the right. And what it kind of gives you is it's actually kind of a matrix of like permutations, right? Those are all the possible combinations of B and C stored in a matrix, right? And so kind of like intuitively, you're thinking to yourself like, yeah, you know, like each of those rows has the same B's associated with them, and each of the same columns has the same C's associated with them. Then like they're probably going to be linear. It's probably not going to be hard to show that they're linearly dependent. So the first assumption I made on the right is that if any of those B's are going to be 0, then the row is going to be 0. And then that would be linear independent, right? Or linear dependent. So we can kind of safely assume that they're not that those B's are not going to be 0 at all. And then
Brian, can you please remind us one more time, what's the goal at the end?
So we want to show that the matrix has rank 1. If B is a 3x1 matrix and C is a 1x3 matrix, and we want to show that their product has rank at most 1. So it's really a general result. But if you think of those matrices in terms of their associated linear transformation, so the number of rows is going to be the codomain, right? And the number of columns is going to be the number of columns is going to be the domain. So a 3x1 matrix has 3 rows and 1 column. And then when we in a 1x3 matrix, we'll have one row and 3 columns. So we want to take their composition, and that's associated with like a linear transformation that is the same, that's going from a one-dimensional vector space, right, to a 3-dimensional vector space. And we want to show that that's what this is saying is any such transformation is going to have be at most rank 1, and rank 1 means the dimension of the range. So you're going to have like 3, like you're going to have basically like, you know what I mean, like it's you're not gonna be onto or you could be 1-to-1, but you're not going to be onto, right? So then, and actually, you know, this might be a good problem to kind of draw a picture for, just to go along with the computations you're doing. But you know, once you get to the part that you can safely assume that you know, any of the B's are non-zero, you can just divide, and then you see you have, you know, after factoring them out. And division here is really the row operation of multiplying by 1 over, you know, by the reciprocal of each of the rows. So, you know, that very clearly has a rank row. But I actually thought, you know, as interesting as that is, I think the next one's even like more interesting. Not the next one, but the next part of it. And is we want to come up with a matrix. We want to say, let A be 3x3 have rank 1. We want to come up with a matrix that represents that, right? Because what we're saying is like, actually, the rank 1 3x3 matrices are isomorphic to the product, you know, to these products. So it's not only going in the one direction, in the other direction, you know, if you have the rank 1 matrix, you can decompose it into right?
Yeah, that's a nice result.
what is it? I just kind of started with, what is it? So A is a rank 1 matrix. That means A is row equivalent to some matrix with only one non-zero row, right? And so if you remember what row equivalence is, and we just started there, and then once you start there, and I actually don't know. Oh, here's my other page. Okay, so I'll bring this up here. So then you can come up with actually what your specific matrix is going to be, you know, in terms of the arbitrary stuff. And I don't know how interesting that result is. I don't know if that.
No, it's interesting. The composition of the matrices is always interesting, especially in application problems. Thank you for sharing, Brian. We don't have that much time. If anyone has question, I wish to answer the questions. If not, I like to leave you in this meeting, and I have to leave because I have class. But I think, Brian, can you stop sharing?
Here, unpin. Yeah.
What is the email about it? Who was talking? Did you receive an email about the virtual teaching and the end date was extended to May 22nd? What is your plan on this matter? Especially, how would you test take home or 30? No, that's not 30%, it's 100% now. Michael? Yeah, this is 100%. I just really take home test and it's 100%. For this test is take home test. And it's just 100% take home test. And then it doesn't mean for the next one I will do exactly the same. I won't. It depends on what is the problem. I may just say 30% is just at home, and another 70% we do it in front of the camera, as most of the teachers do. But it depends. It depends. For now, I have made 10 problems 100%, and it's all take home test. Any other question? That would be a really good idea. I know you have only 1, 2, 3, 4. 4 of you are here, huh? So that would be a good idea if only 4 of you are here. Just practice some other problems. Okay, so let me close this. No. Okay. I was trying to share something. If I can find, this is you, this is 307, this is me, this is exam number 2. Then I don't know, this is take home test that we have had last time. What did it ask us to do? Okay. Since only now 3 of you are here, okay. If you have to, I have to leave. I don't have time to stay. But if you have time, you can just start to practice these problems. I don't know how many of you have access to this problem. This is for last semester. Okay, that was just take home test for last semester. If you can just stay a little bit to work on the problems, it's just really up to you. You don't have to, okay? So in this case, I have to leave, and then we can practice the problems. Any suggestion for what? Okay. Was it the old question? you know, your test is just really combination of your assignments. It's not really something that is, I don't think is really any surprise. It's really a combination of your assignments. So the lecture tells you what you need to do, what's the process, and then the way that if you have done your assignment by yourself, I don't think the test is any surprise. Okay, so that's just really something that somewhere you have practiced. And as I said, I try to put equally just every single section have at least 2 problems. Every single section has at least 2 problems. Means, for example, if you have changing basis, so that's 1 problem. If you have invertibility, that's just 1 problem, 1 true false problem, 1 proving problem. And then there are some computationals, like just really problem number 1. So there are 2, what is transformation, you write matrix transformation and you just write the composition of them. It's really computational. And then the proving thing. Okay. Anyone interested to stay more to do with your friends, or I just need to disconnect this one? It's just really up to you. You too, Michael. Anyone staying to discuss without me? No response. Okay. So if no one is staying, I'm going to end the meeting. So, and then this is recorded, and then you can have the problem to practice later, or I can send the problems. That's not a big problem. Okay, so I will send the problems for you to practice. Bye, guys. Have a good day.